Hello everyone and welcome to another lecture. So in the past lecture we saw how we can try to develop a formal procedure to solve a coupled differential equation or a system of differential equations, and today we are going to work that out. And if you recall, our coupled differential equation or the system of differential equation had the general form like this. This f was the non-homogeneous term, and we will only consider the homogeneous equations. That means f of t or this f will be 0. So our equation will now be something like x prime a x, right? And now we want to solve it. So if you recall, these were column vectors. Obviously I'm not using the bracket notation for convenience, because since you are dealing with differential equation, if I use the bracket notation you might get a bit confused, so that's why I'm not using it. So these are our column vectors. This was the matrix, and this matrix contained this p1, p2, pn, q1, q2, qn. However, we are going to consider constant coefficients only for simplicity, because there might be cases where if the functions, these p's and q's, if they're very complicated, it might not be possible to solve the differential equation analytically. So that's why we are considering only constant coefficients. So now, since we are considering homogeneous differential equations with constant coefficients, what we can do is that we can make an analogy with the differential equation that we solved before, and we can seek solutions in the form of capital X is equals to v e to the power rt, where this v is a non-zero constant column vector. Now if you use the definition of X, that is the type of solution you are seeking and the type of equation or system of equation you are trying to solve, if you just combine these two, that is, let me just use another color, combine this one and this one, you will get the following. That is, this is the equation that you are trying to solve, and you are seeking solutions as v x equals to v to the power rt, and from here we will get the interpretation of r. So x prime will be just, since v is a constant column vector and r is just a number and t is the independent variable, and this prime means you are differentiating. Let's say your x is something like this, x1, x2, and when you take a prime of this, this means you are differentiating element wise, just like you did in the function of matrix when we did linear algebra. So since this guy is a constant, it will just stay there, nothing will happen to it, and only e to the power rt will get differentiated and it will speed up an r. So this will just be r v e to the power rt, right? So let's write that as x prime r v e to the power rt equals to a x, but x is what? V e to the power rt, right? And this e to the power rt is not 0, and what we can do is that you can take this guy onto this side and have a v minus small r, that is a scalar or a number, whatever you want to call it, and capital V, and this is equals to 0, right? So this means, and also e to the power rt is not equals to 0, that's the condition. And now from here you can see that AV is equals to RV. Again, this A is a matrix, this is a column vector, this is a number, this is a column vector, and this is precisely the eigenvalue equation. And these V's are the eigenvectors of operator A. So V, they are eigenvector of A, and R denotes the eigenvalues. So ultimately, solving a system of linear differential equation with constant coefficients boils down to solving an eigenvalue equation, and using these eigenvectors we can construct our solution. So let me just move forward with an example so that things are very clear to you. We'll see two examples, and the first example will be where we can see some real and distinct eigenvalues, and the equation we are considering is that x1 prime is equals to 3x1 plus 4x2, and x2 prime will be 3x1 plus 2x2, and we have our initial values. This is the initial value problem, so we are also having some initial values over here, because if you don't use an initial value you will get an arbitrary constant. If you get a initial value, then you can find the values of those arbitrary constants. So that's why I consider this thing, so that I can show you the general solution and the solution where the arbitrary constants are determined. So this is our system, this one on the left hand side, and this can be written as x1 prime, x2 prime, that is in a matrix manner like this, 3 4 3 2, and you have x1 and x2, and you can check and match that this actually works. So now denote this as capital X, this as A, and this is capital X. Sorry, this one is capital X prime. So again you have this form, capital X prime is equals to A capital X. But we saw that we were seeking solutions in terms of the eigenvectors of the operator and the eigenvalues. That is, the eigenvalue goes in the exponential and the eigenvector sits there. So the first thing we are going to do is that we are going to find the eigenvalues of A. So eigenvalues of A. So if you recall that if you have eigenvalues as R, this will be just the characteristic equation will come from this, where I is a since this is a 2 cross 2 matrix, this is a 2 cross 2 identity matrix. So I'm just gonna write down directly that it has 3 4 3 2. So from the diagonal elements I have to subtract this R, right? Okay, and we have to make this determinant 0. So now we get 3 minus R, 2 minus R, minus 12 equals to 0, and this will give us an equation. If you just simplify it and multiply it, this will give us R square minus 5R minus 6 equals to 0. This means R minus 3, oh no, sorry, not minus 3, it should be rather minus 6R plus R minus 6 equals to 0. This means R minus 6 and R plus 1 equals to 0. So the two eigenvalues are R equals to 6 and R equals to minus 1. So we have found our eigenvalues, and now we want to find the eigenvectors. So let's try to find the eigenvectors now. So if you recall how to find the eigenvectors, is that, let's say I want to find for R equals to 6. So what I'm gonna do is that we had a 3 over here, so it will be 3 minus 6, it will be 4, it will be 2, this will be 3 and 2 minus 6, like this, and there will be this x1 and x2, right? 0 0. So this gives us minus 3 4 3 minus 4, and x1 x2 equals to 0 0, and finally you will have minus 3x1 plus 4x2 equals to 0, and 3x1 minus 4x2 equals to 0. So these two are basically the same equation, right? And if you just express x2 in terms of x1, one of them will be the ratio of other. So the best idea is to just use one of these equations. Let's say I'm going to use the second one. This tells me that 3x1 is equals to 4x2, and I can say that x2 is just 3 by 4x1, right? So the eigenvector, let's denote it as v1, which corresponds to r equals to 6, will be just 3 by 4 x1, and this will be x1. And now I can take any value of x1, and I can even normalize it, but I won't bother with the normalizing. It really doesn't matter. So let's take x1 equals to 1. You can take any value you want inside it, because this is like a free parameter. You have two equations, and you have two variables and one independent equation. So this x1 is independent parameter, so you have 1 over here and 3 by 4 over here. Now you can make things look nicer by multiplying it with 4, so that will give you 4 3. Now you might say, why am I doing this? It's allowed, because it's just rescaling the vector, and it really doesn't affect anything. It just scales the vector, it doesn't change its orientation. So one of the eigenvector, let's call this v1 as before. This will be just 4 and 3, and the other eigenvector that comes from the value minus 1, the eigenvalue minus 1, that will be just minus 1 and 1. So now how do you write the solution? So the full solution is written as this x, where you have c1 v1 e to the power r1t, c2 v2 e to the power r2t. That means a linear combination of the solutions for the variable x1 of t and the variable x2 of t. That's how you write the full solution. And obviously these are column vectors, this x1 and x2. So if I just write down the full solution, this will just be how do you say this? Yeah, you just have to write down the numbers. So let's say r1 equals to 6, so that will be 4 3 e to the power 6t plus c2 minus 1 1 e to the power minus t. That's it. And you can use the values over here, this x1 0 and x2 0, that is these guys, to determine the coefficients that appear over here. So this capital X, if you recall that it had x1 and x2 like this, right? And now what you can do, you can just put or you can even write it like this. Let's say 4 c1 e to the power 60 plus, that means I'm writing in a compact matrix form, I mean a column vector form. So there will be plus and there is a minus over here, so that's minus c2 e to the power minus t, and x2, oh no, sorry, not x2, and it will be 3 e to the power 6t, and there is a c1 over here multiplied with, so, and here you will have a c2 e to the power minus t like this. So this is your x1, this is your x2. So you can write x1 of t as 4 c1 e to the power 60 minus c2 e to the power minus t, and you can write x2t as 3 c1 e to the power 6t plus c2 e to the power minus t. And you have some initial values, that is, let's say x2 of 0 equals to 5 that we saw. So what you need to do, you need to put t equals to 0 over here and put x2 equals to 5 on the left hand side. So 5 will equal to 3c1 plus c2. Similarly, x1 of 0 was simply 2, and x1 of t is over here, that is this line. Again, you put t equals to 0 over here and 2 on the left hand side. So this will mean 2 equals to 4c1 minus c2. Now you can easily solve for c1 and c2, because if I just add these two equations, I will have 7c1 is equals to 7. That means c1 equals to just 1. And if c1 is equals to 1, then I'll have 2, then 4 into 1, that means 4 minus c2. So that will mean c2 is equals to just 2. And you are done. This is how you can solve this simple system of differential equations with constant coefficient and which are homogeneous. Now there might be cases where the eigenvalues are complex numbers, right? So that's why we're going to see another example today, and this example will involve the complex conjugate eigenvalues. And note that today we are discussing only the type of solutions that is only valid for the non-degenerate case, that is the eigenvalues are not repeating themselves, and we will see how we can deal with repeated eigenvalues. That means whenever there is degeneracy, we will see how we can deal that in the next video. So in this example, I'm going to give you a spoiler that the eigenvalues will now be will come in terms of the complex conjugated terms, that means complex eigenvalues. So without further ado, let's just write down the differential equations as minus x1 plus x3 and x2 prime as minus 2x1 plus x2. And I'm not gonna consider any initial condition right now, because I just want to, because that's quite easy. You just have to put the values of t and you have to find out the arbitrary constants. So again, if you just write them up like this, obviously it's not necessary to write every time like this. I'm just showing you for your convenience. So this is minus 1, this is 1, minus 2, 1, right? So our eigenvalue equation, that means determinant of minus 1 minus r, 1 minus 2, 1 minus r, this will be 0. That is the thing that will give us the characteristic equation. And if we do that, this will just be minus 1 minus r times 1 minus r minus, there's a minus 2 and this will cancel each other out. So that's how it will be. I can take another minus out. This will just be minus 2. And sorry, the 2 won't cancel, only the minus sign will cancel each other out. So yeah, and this is just 1 minus r square is equals to 2. So this means r square is equals to 1 minus 2. That means minus 1. So r equals to plus minus square root over minus 1, which just means plus minus I. So we have two eigenvalues with, let's say, r1 is equals to plus I, r2 equals to minus I. So how do we proceed? We proceed the same way as before. The only difference is that since we have this exponential and we have some imaginary number now, if we want to write our solution only in terms of real variable, we have to use the Euler identity. That's why I just wanted to show this thing. Other than that, it's similar to how we dealt with the real eigenvalues. So now we want to call up our solution, the capital X, and before that we also need to find the eigenvectors, right? So let me just show you the end result of the eigenvector thing, that the eigenvectors, because you already know how to find the eigenvectors, so the eigenvectors for, let's say, the eigenvalue is just one of them is 1 plus I, and the other one will be 1 plus I as well. So now we see that there are these two eigenvalues, and as before we are going to find the eigenvectors, but now there is something else, and that is that since we are only dealing with real numbers, we can only construct real solutions. So that's a constraint. However, if you don't have the constraint, then you can keep up these exponential numbers and all that. And if you now solve for the eigenvector, you can get a basis eigenvector as 1 and 1 plus I, like this. You can verify it easily. So after that, what you are going to do is that you are going to construct a real solution by using Euler's formula, that is the Euler identity, this one over here, and we are only going to keep the real part, because if you are restricted, if you are not restricted, you can keep the imaginary part as well, but if you are restricted, then you have to keep the real part only. So our first solution will be, let's call this as x1. It will be the real part of this. Obviously I'm ignoring the arbitrary constant right now, and we'll have e to the power it, like this. And if you expand this in this using this Euler equation, this will just become cosine t and cosine t minus sine t. Okay, and the other part, let's call it x2. This will be the imaginary part of 1 plus I e to the power it, like this. So again, this will be just, it's like just taking this thing and just boiling them into real and imaginary parts. So if you do that, this will just be, you have to obviously calculate it using this Euler identity, but that's pretty simple and I'm not showing it over here. So this will be just cos t and sine t, like this. And you can now use these two construction to solve the general to make the general solution x of t, which is again a column vector, and as c1 x of 1 that we constructed over here, and there is this x2 c2 x2, like this, and this is your general solution. And this c1 and c2 can be evaluated if there are any initial data. So that's the idea. So whenever you have a system of, I have only showed to you that the 2x2 systems, but this will also work for any n cross n system that is homogeneous and the coefficients are constants. That is the equation that look like, okay, let me find the equation. The equations that look like this. Instead of 2, you can have 3, 4, 5, 6, blah blah blah, and there will be some coefficient matrix and there will be another column vector. So this is how you can formally solve system of differential equations by using the techniques of linear algebra. So this will be it for today, and I'll see you guys on the next lecture. Thank you.